Okay, good afternoon, everyone. So this week we have one of our members, Hazal, as our speaker. Hazal is doing her PhD in our department, working with me and Fatih Hoca. She received her bachelor and master degrees from our department as well. And currently she's working as a teaching assistant in our department. And her main research interests have been and are computer vision, signal processing, fMRI analysis, and currently she's working on disentanglement, which is the topic of her presentation. The screen is yours, Hazal.
Thank you very much. So, hello everyone again. I am Hazal Mogultay. Today I will be talking about disentanglement. So let's start. In case you haven't heard it before, according to Cambridge Dictionary, disentanglement is defined as to separate things that have become joined or confused. So to be on more machine learning side, we came up with another definition. We define disentanglement as learning a data distribution such that the underlying sources of variation that generates the data is learned in a compact way and they can be examined independently. So if you consider this example, let's assume we are given a training data set like this consisting of 9 shapes, and we are interested in classifying the emotion of these shapes, so surprised or happy. You can see there are other generating factors of this data sets like the eye color, the color of the shape, or shape itself as circle or rectangle. So we are trying to classify emotion of the shape, but you can see there is a bias in this data set. For example, all of the rectangles, most of the rectangles here are surprised. So this can affect our machine learning algorithm. So if we can separate these generating factors like color or shape, our algorithm can work in a better way. So now let's consider an example from another paper addressing the topological defects of disentanglement. By the way, throughout my talk, you can see all the references at the bottom of the page. Let's assume we are given some dog images data set. The generating factors can be listed as pose, color, or breed. Of course, we can list many more attributes, but for now, just focus on these 3. In disentanglement, given this data set, we are looking for encoders, like a mapping function, to a representation space such that this representation consists of subgroups corresponding to pose, color, or breed are generating factors. And these 3 should be independent from each other. From this example, they define disentanglement as isolating statistically independent factors of variation in data into independent latent dimensions. So if we take a look at the history of disentanglement, beta variation autoencoders are like one of the first methods to achieve disentanglement. You may already know that in standard variation autoencoders, we have an input and output space. We try to encode the given input to a hidden representation, and then we try to decode and acquire the image itself. In variational version, we represent hidden representations as a Gaussian. So our loss function is like a reconstruction loss and an additional term, Kullback-Leibler divergence, which is like forcing this hidden representation to be closer to the normal Gaussian distribution. And this weighted term is actually where the magic happens. Forcing this function here, forcing this distribution to the normal, makes sure to acquire independency within the latent code, so that each independent factor here in this latent representation actually represent any other sources of variation in our original data set. So these are some results from the original paper. These independent representation subspaces can encode skin color and gender and age. I am not saying these are perfect results, but they are good in disentanglement. So for now, let's consider the bottom row. In the skin color, we can see, by the way, in this representation, since this is a Gaussian, when we sample, for example, from here, we can walk on this Gaussian and change that attribute and that attribute only. So we are walking on this Gaussian distribution and slowly changing the skin color of the person. Or we can slowly walk on the distribution and slowly change both the age and the gender. So beta variation autoencoders were very good and they increased disentanglement. However, while doing so, they also increased reconstruction loss. But there are many different other models and other variations of variational autoencoder that has achieved disentanglement. I will not go into the details of those. In this talk, I would like to talk more on the theory and metrics of disentanglement. So I want to make sure you understand it and feel comfortable to use this in your studies. So if we look at the theory, Higgins et al. Provided a formal definition in 2018 on this topic, but this definition requires a knowledge on the group theory. I will not go into the details, but I will talk about a more recent paper that also provides a formal definition on disentanglement. This paper called the Addressing the Topological Defects of Disentanglement. Before going into the definition, I would like to consider disentanglement. And while I'm defining disentanglement, you can check on this example. Let's assume we are given a data set of digits and we are trying to disentangle transformations from object identity. So if we are given a digit 4, even if we rotate it, the identity, the digit should not change. So the identity and the rotation should be independently represented. So this is the definition. This is again based on group theory. We are trying to find a transformation group G, which is factorized into subgroups. You can think these subgroups as transformations such as G1 can be rotation, Gn can be shift. These are acting on original data samples. So we can rotate our original image. So these are, their intersection is empty. So we are looking for a representation. This function is called the encoder in our machine learning terms. We are looking for a representation, disentangled representation based on this group definition. So our representation is disentangled if the model includes this operator, such that this operator corresponds to subgroups, each of these rotation and shift, acting on the entire representation space. So we are looking for this mapping. Right now, I know this definition does not make much of a sense, but let me explain it in other terms. So we are given some transformations and we are trying to disentangle them from identity. So what does that mean? Let's consider this bottom left example here. We can say we are in an original autoencoder architecture. We are given an example here, sample image. We can rotate it and our autoencoder should produce the rotated image itself. So this function here represents this. We are given an X and we are applying rotation on it, and then we are using our encoder. So if we can find a mapping such that given an image to an encoder and then rotating, applying an operator on the representation space and then decoding it, produce exactly the same output. We didn't change the identity, we just changed the application of the operator space. So if we can find such a mapping, we can say that we are disentangling identity from translation. So in order to find such a model, it should respect to the structure of the data and its transformations so that the learned space Z should preserve the entanglement between factors of variation. What does that mean? That means we cannot disentangle everything. So why did they came up with such a complicated definition? Because they compared some other disentanglement models, such as beta variational autoencoder here that I have talked about before. They trained them on a single-digit training set and looked for the rotated outputs, tried to learn the rotation within the encoder. So if we train them on single-digit data set, it works fine. It can rotate the image. However, if we train it on a multi-digit data set, we can see that it cannot disentangle the digit and its rotation. For example, the 4 here became something like 3 or 8 here and the 2 here. This means the rotation and identity is not disentangled. So this is something that you should be very careful when you are using disentanglement in your studies. So why did they make such a complicated definition? They give this example. Let's assume we are working on only 3 pixel images. So the first row consists of 1 pixel wide images, 2 pixel wide images, and 3 pixel wide images. And these 3, first row, these 3 are actually the translated versions of each other. So in terms of topology, I'm not an expert on these topological definitions, but they say in terms of topology, these 3 creates an orbit in the representation space. So what do we exactly, we are trying to find a mapping from this space to a latent space such that it can consist of 2 different parts. This ZI here is invariant to transformation. It only says you how many black pixels are there in your image. And this ZE encodes the transformations and said that where is that black pixel. So let's consider here in our original space, the blues, oranges, and red ones are scattered like this. Since all of these 3 black pixeled images are exactly the same, they are mapped into the single points in our data set. So we said we are trying to find a mapping. So all of these orbits should be orthogonal to the ZI space. Why is that? Because ZI doesn't have any information on the transformation. It only says how many black pixels, which orbit are you working on? And on the other hand, And on the other hand, this encoded transformation encoder space should be parallel to each other. If they don't, you will leak some information on the ZI. ZI will include some information about the transformations. So when we look at this picture, we see that our single red dot here should be encoded into 3 different points. So if we think in terms of mathematics, this function definition is impossible, right? So they say we cannot find a good disentanglement based on these variational autoencoder definitions because this mapping can create some discontinuities in our representational space. So we cannot make this disentanglement. So what can we do? We can enforce our original definition on the model. Rather than trying to learn all the transformations in the encoder, we can create a transformation operator and enforce it on the representation space. This is exactly the same how we defined the disentanglement before. We can define our transformation operators such as single rotation matrices or scaling matrices, and we can concatenate them. We can basically select anything we want here. And when we look at the results, by the way, these results are trained on multi-shape data sets, and we can see that they rotate the images, the shapes, quite well. Okay, saying that, I have to say that this representation, this definition came out at 2021. However, other studies have been using it before implicitly, without defining formally. Let's consider the hologram model. In this model, they are trying to disentangle the pose identity, shape, and appearance. They are using a constant vector, and by some stacked convolutional layers, this is a generator, they are generating an image. And here you can see they are enforcing a transformation in some of the middle layers. So it can say actually hologram follows the same idea implicitly without formally defining it. And when we look at their results, they are quite good. For example, this cat, we can see changing the pose of his head quite nicely without any noises in the images, or we can see the same thing on the celebrity faces. And these results are from 2019, 2 years before that definition. So that's, I think, enough for theory. I will continue with the metrics. So how can we define how to measure disentanglement? How much disentangled are these two representations? There are many different metrics defined in the literature. These are just some of them. I will not talk about these, but if you are interested, these are the papers you can check to start the literature, and you can find some comparisons among the metrics as well. Again, as with the theory, I would like to talk a more recent paper on metrics. It's from 2019. First of all, they define disentanglement as a process of decorrelating information in the data into separate informative representations. Each of these separate representations correspond to a concept defined by humans. So when we disentangle two things from each other, for example, one of them should correspond to the eye color or hair color, I don't know, something defined by humans. So, and they say disentanglement has three important properties: informativeness, separability, and interpretability. By these two properties, they define some metrics actually, and these are really simple to understand. Let's go over them one by one. If we want to measure the informativeness of our method, we can simply compute the mutual information between our data point and our representation. So let's consider this variation autoencoder architecture. If our representation space is informative, it should have high mutual information between the dataset. Let's continue with separability and independence. We said that each of these subspaces in representation should be independent from each other. We can compute them by, again, using mutual information. We can say that mutual information within any pair of these representations should be 0. Or we can compute multivariate mutual information between X and any pair of Zi and Zj, and say that the multivariate mutual information should be 0, which means Zi and Zj are separable and they don't share any common information about X. So informativeness, we can measure informativeness, interpretability. We can measure interpretability again with mutual information, but it requires some attributes level labels. So we need to know how much rotation we have in our shape, for example. Assuming this y is the labels in our data set and we are given that, if our zi subspace is interpretable by human eye, the mutual information between this one and the label should be high. So they also say that in real data, factors are correlated. For example, in faces data set, only men having beards, for example, in celebrity attributes, celebrity face attributes data set. So for good interpretability, we should isolate the factors and process one at a time. So we should process man at one time and beard at another time. This can mean two things. Isolating these can decrease the dataset bias if controlled carefully. But also it can mean we cannot disentangle these two. So if these two are entangled, this shouldn't be man and beard. This can be gender and the identity of the person. If they're entangled and we are trying to separate them, we can lose so much information and our model would not work. So this is something you should be careful when using disentanglement. So that's all I want to say about these metrics. They define many other metrics by the combination of these three definitions. But what does these metrics measure brings us to the topic of models. Actually, I've been reading a lot on this disentanglement and I'm trying to make a taxonomy on the models. So basically, we are separating implicit models and explicit models. Implicit models, you can consider the beta variation autoencoders. It finds independent factors. We cannot say what factors will be learned within those subspaces. In explicit models, you can consider the transformation sample example that I gave before, that they were enforcing the transformation on the latent representation. That was an explicit model. And we can say, this is by the way, original. We can list many other models here. I will not go into the details of this, but I will be giving some examples on the models. There are many different models in the literature if you start checking. So I would like to start with StyleGAN. This is from 2019. If you haven't read it, I would really recommend you to read it because their results are really good. In the traditional GAN architecture, they are taking a latent representation, the noise representation, and while upsampling it, they generate an image. However, in StyleGAN, they use the ADAIN features, and from a noise vector, they use some fully connected layer and find the representation, find the V matrix actually. And these matrix is used as the features to the ADAIN here. And we can use it after every convolution. And at this right-hand side, they are feeding some noise after every convolution again. So they show that this ADAIN features can actually disentangle some information implicitly in the data set. So these are the results from StyleGAN. So they are taking some attributes from source A and some attributes from source B and look at the output of the generator and say that if you look at this here, if we are copying styles from coarse resolutions, we can get attributes such as pose, hairstyle, face shape, and eyeglasses. For example, this column here all have eyeglasses because the eyeglass attribute is coming from source B. Or some other results, if we copy styles from middle resolutions, we can get facial features, hairstyle, eyes open or closed. Or let me see if I can give you some examples. Oh, okay, we can see again eyeglasses here, but if we take a look at here, we can say that the hairstyle is almost similar in all the outputs here. By the way, if you haven't heard, StyleGun 2 is published. I didn't have time to read it yet, but I've only checked the results, and they are really, really nice. I again recommend you to check this one if you are using these kind of methods in your research area. So what about our models? From now on, I will give you some other models. I will talk about some other models, but I will not go into the really detailed loss functions and optimization, everything. I just want to give you some idea and some opinion on the available models. So we have the problem of face identity disentanglement. I would like to talk about this model. When I first look at the results, I was really impressed because the outputs were really, really nice. Then I dive into the details of this model. So they are taking two examples in the training procedure and feed them to different encoders. The first encoder here learns the identity of the given image, and the second one here learns the attributes. And in the middle layer, they are using StyleGun as the generator. They are taking the features acquired from these two encoders and concatenate them, and then feed them to StyleGun. And they use some other losses. For example, this LID here is used to make sure that the output and the first image in the input have the same identity. And all of these other losses do such measurements in the loss function. When we look at this, we expect our model, this model, to disentangle identity from all other attributes, right? So let's go back to our outputs. So we can see these good results. I think they are mostly because of they used StyleGun. You remember the outputs of StyleGun here? They were really, really nice. And the reason they have good results, and I think this is my opinion, is thanks to this StyleGun. So let's see how can they disentangle. So they say the first row here represents the identity, and we are taking the attributes from this column. So I would expect identity should remain same among columns, but attributes should change. But only changed attributes are how much the mouth opens and the pose of their head. For example, they didn't even disentangle the eyeglasses attributes. So in most of the models, they say they try to disentangle eyeglasses from identity because these two aren't related. You can simply take off your eyeglasses, but your identity wouldn't change. So I would expect to change in the eyeglasses here based on the attributes we are taking, but they didn't. So this can say one thing. The definition of attributes is so vague here. They don't say specifically what attributes they are trying to disentangle. So we just expect all of the other attributes to be changing. So when you are working on such a work, you should be carefully design and define your attributes. What are you trying to disentangle from each other, and can you disentangle them? So let's continue with another problem definition. Let's continue on image-to-image translation in unpaired setting. So we take one image from one data set and one image from another, and we are to translate one another, but we don't have any paired supervised labels. So in this example here, we are trying to take male images on one data set, and on the other, we are taking female images with makeup, and we are trying to actually put on makeup on male images. So in original autoencoder architectures, they simply change the gender of the given image. Since most of the samples in the second data set are females, they change the gender of the first data set. But we don't want that. What we can do is we can simply disentangle makeup and gender from each other, and then use only the makeup subspace of the representation to affect first data set. It is actually shown here. It's better to go over this one. We are trying to go from no makeup males to makeup males. Our standard models take these examples and put them here, females with makeup. And if we can disentangle makeup and gender, we can actually go directly from right here to right there. So this also says that we can eliminate the dataset bias in our models. So let's go to the outputs of this model. I didn't tell you about the model because the outputs were not really good. So, but let's just say image-to-image translation is one of the problems that you can use disentanglement in. This again, another image-to-image translation model, and it is actually better than the previous one. They are taking these input images taken in winter, and they can slowly translate them into summer pictures. So what other problems that we can solve with disentanglement? There's dehazing that you can use FDGAN, and of course there are several other models that solves the hazing problem. And if you have some videos or some time series information, you can use in their classification or frame generation by using disentanglement. Actually, you can disentangle the objects and their, as in the beginning, their transformations. And by using this time series information, you can simply generate the next frame. Oops. This is another problem. This is face hallucination problem. This is the results they acquired with PEC. So I'm just listing some other problems that you are using. So I've just named a few. There are many different models proposed in the literature that are used to solve several different research questions. So if you aren't using disentanglement yet, maybe you think to consider using it if your data set has something to separate, and separating that helps your model to improve. Maybe you can consider disentanglement after this presentation. But if you try to use it, be very careful on the models, because most of the models and most of the metrics are defined based on the problem definition, and you should always be careful about which attributes to disentangle. And there is still an open question to whether we can say these attributes are entangled and disentangled, whether we can measure somehow which attributes are entangled. Actually, I'm working on this problem. This is exactly the same. So again, I say the metrics are problem defined, and it can change whether you have the labels or don't. Or you can push some metrics as a loss function in your loss function. So I don't know, many different things that you should be considered, but the results are really important. So thank you, but I would like to say I have been reading a lot of papers in disentanglement. So if you are not sure whether you should use it or not, or how you should use it, or whether your data set is applicable to disentanglement, you can always contact me. I will be very, very happy to help you in that area. Thank you.
Thank you, Hazal. That was a really nice presentation. So what are we seeing here on the slide?
These are called disentanglement puzzles. These are actually some metal toys that you try to disentangle.
Okay. Any questions from the audience? Father Shoja is applauding you. Maybe I can do that as well.
I can ask. I'm curious about something if nobody is asking. Hazal, in Higgins group theory, you talked about a function phi, or was it phi? I'm not sure. About transformation applied in an autoencoder setting. It's not clear to me if the encoder and decoder part are the same. I mean, without applying that translation function to the Z. Can you clarify that part? I don't know that part, that's why.
So you're asking this encoder and this encoder are the same or not?
Are they the same? Are they a decoder also?
Oh, decoders are exactly the same. You can select them, or of course you can change them if you want based on your problem settings, but you can simply set them as the same. Actually, the same goes for encoding too. Because in our encoding architecture, okay, let me put it like this. So we are trying to disentangle identity and translation here, but there are some other factors of variation. So if we want our encoder to disentangle them somehow, disentangling them improves our model, we can use a variational autoencoder here, or we can use simple encoder here that is not disentangling anything.
Okay, so this one says that however you rotate Z, whether you use it directly or you rotate it using an Euclidean transformation or affine transformation, whatever. It's not affine, I guess, but maybe. You showed the transformation matrix before. I think you are applying such a transformation here. Then still the same decoder can produce but what is not clear to me is a particular transformation that you put at the end is a bit confusing to me. I was just expecting that whether you provided rotated version of that, I would expect it to generate the same identity instead of rotated version. I mean, this is a bit confusing. Maybe it is in the paper, I don't know, but
I think you are talking about this part here. We are enforcing this phi something here.
Yes, but isn't it the same?
Yes, but this is different from the operator that we use on the original image.
But I think in what you write here on the right, it's just rotation matrix. This is rotated.
Yes.
I mean, it looks conceptually the same to me. At the end, it is showing rotated version of that one. Okay, maybe I should just read the paper. Some parts are not clear to me. I also want to comment on something because I need to go in 5 minutes, as I said, there's another meeting. Sure. Disentanglement, this is just comment. For example, we also work to find some factors of variations, but we didn't assume that the vectors that components of vectors that are orthogonal to each other. I mean, in the definition of disentanglement that you presented in some papers from the literature, some of them try to find zi's, z1, z2 as a vector, right? And they are not related to each other. They are orthogonal. I mean, if you are changing one going in one axis, other factors are not changing. So there's an independency definition there. What we observed in our work, and I will present it maybe later soon, there are also, I mean, factors of variations in different directions, and they are not orthogonal to each other, but you can still define them. I just want to say this to you. Maybe you can also consider those aspects of disentanglement. I don't know if I am made myself clear, but maybe after my presentation it will be more clear, because it's really hard to find those independent components, as you said, from the dataset biases. Usually those axes are related, correlated with each other. So if we cannot disentangle from axis level, can we find directions that factors out the variations, other variations that change only one factor in your data set? This is actually what I'm more interested in. And they are not also handled in these works. But still, I mean, these works also, I mean, this rotation thing using variational autoencoder, I find it very interesting also. I will really thank you. It was really a good presentation.
Thank you for your comment. I will definitely check those terms in terms of going along one axis or one direction.
Yeah.
I don't know them quite well, but I will definitely check. Thank you.
Okay, thanks.
Any other question, comment? Maybe I can continue from where Georgia talked about. So here, these psi functions are actually, they can be any function, right? Because they are acting on the embedding space on which we don't have any idea. Any one-to-one function there is actually fine, right? Is that the case, or is there? Do they have some constraints on what psi can be?
Can you repeat? I don't think I understood your question.
This function acting on the embedding space.
Yes.
To rotate the embedding. Are there any constraints on what kind of function it should be? I mean, could it be any arbitrary function?
They only define these functions in terms of transformations, these rotations and shifts. As far as I remember, they didn't mention any other functions.
Okay. Regarding Hatice Hoca's comment on orthogonalization, I think orthogonalization might be a too strong constraint, and it has been shown in some papers that are trying to enforce orthogonalization. They couldn't obtain good results, so they couldn't disentangle some variation directions. So maybe we should look for some other constraints, and actually some constraints might be easily satisfied by some attributes, like, for example, male and female, but male and beard cannot be easily disentangled. So you cannot enforce orthogonalization for some attributes. So maybe in this regard, we shouldn't consider all attributes in the same manner. So attributes have different types of relations between them. And I think we should consider those relations while disentangling them. Maybe the embedding space should be a hierarchical space that can allow such types of interaction. Maybe at the higher level of the higher levels of the hierarchy, we can enforce orthogonalization, but at the lower layers or nodes in this along the same path, maybe we shouldn't enforce orthogonalization. I think these are important things to consider.
I think this brings us to the previous question. What can we disentangle? Are they entangled? How should we define entangled attributes? What is the relationship amongst them? It can be defined based on the model itself. I said this was an open question.
Yeah. And the three constraints that you talked about, mutual information, independence, separability. I think in fairness, in studying fairness, they talk about similar three constraints in defining what is fair. And there is a proof that more than two of these constraints cannot be satisfied. So you can satisfy only two of these constraints. I'm not sure whether it is the same in disentanglement as well. So can we satisfy all these three constraints? I think it would be nice to check the relations of these constraints. I think they are very, very similar.
Actually, in the talk, I said they are proposing some metrics based on these three definitions. They are using different combinations of these. So somehow they can use this informativeness and separability, or separability and interpretability. They define like 8 or 9 different metrics actually based on these three.
Okay. Any questions from the audience? If not, we can stop recording and continue informally. Okay, let me stop recording. Thank you, Hazal, again. That was a very nice presentation. We will continue informally.